All right, we're recording. So today's lecture is going to be about equivalent statements. I don't have my stepson Byron here with me to act as a surrogate audience, so this time I'm talking just directly to you. All right, so we deal with equivalent statements in mathematics and really in life all the time. So, what does it mean for two statements to be equivalent? It essentially means that you're expressing the exact same bit of information in two different ways. So if I were to say I own a red dog, and if I were to say I own a dog that's red, those would mean the exact same thing. You would get exactly the same information from hearing those two sentences. So in mathematics, our equivalent statements tend to be something more like this. So again, in the knowledge of numbers and variables and algebra that we might be more familiar with, 2 times x plus 3 is equal to 2x plus 6. All right, so more likely than not, we're all familiar with this statement or some things like it. And if you were to be asked why this is true, you'd say, well, this is the distribution law. This is a sum inside of parentheses. I got a product, so I get to multiply that factor through. But that's a rule that's that you memorized or was established earlier in your learning. But what does it really mean that these things are equal? What does that equality here really mean? Well, it means that for every single possible value of x, if I put x in there, put x in there, that this statement will have to hold, that the value I get from here and the value I get from here must be the same. So if x is 1, then 2 times 1 plus 3 is 2 times 1 plus 6, which is 8. That's 8. That's 8. They're both 8, so they must be equal to each other. Right? If I say x is negative 4, then 2 times negative 4 plus 3 is going to be negative 1 times 2, which is negative 2, and 2 times negative 4 plus 6 is negative 8 plus 6, which is negative 2, and so on. So, um, what this means then, I'm not going to obviously do every single possible value of x, but what we know is that given every possible value of x, if I evaluate both sides at that value, we will get the same thing. Now, for typical algebraic expressions like these, um, you have to check the equivalence in methods other than just plugging in numbers, right? Because x can take on infinitely many values, and so there will be infinitely many things to check. And this thing could have infinitely many values. This thing could have infinitely many values. And if you were to try to do this by exhaustion and going through all the possibilities, that would suck. But in this chapter, in the world we're living in right now, we don't have infinitely many values. We have two values, true and false. And since those are the only values that we have, we can actually use that and methods like that in order to evaluate equivalence between statements. So fundamentally, two statements are equivalent if they take on the same value under the same circumstances. Let me get out of the way there and see if you can read that. you're all going to be glad that I type up notes for you guys when you start reading my handwriting on these lectures. So two statements are equivalent if they take on the same value under the same circumstances. So that's the equivalent idea to over here. The same circumstance means the same x value, and then the value that the statements take on are the things that we get from evaluation. So let's give an example of two statements over here, and let's ask ourselves if they are equivalent. So is not P or Q equivalent to not P or not Q? All right, here's a statement, here's a statement, and what we're asking is, are these two statements the same? I have not P or Q, and here I have not P or not Q. So before we jump into the formal symbol pushing aspects of all of this, it would help to concretize this a little bit and just see intuitively, does an equality of these statements make sense? So remember, in mathematics, like in all things, before you get into like scribbling down symbols and messing around with equations, it always helps to take a step back first and ask yourself your gut intuition if these things should be the same or not. And one way of doing that here is by attaching specific values to P and Q. So I got some colors here. Let's pick one and ask. I wonder how orange will show up on this thing. So let's give P and Q some concrete values. And so let's go with the, that looks terrible. Better. Okay, so let's say P is a statement, I will eat breakfast, and Q is a statement, I will eat lunch. These served us pretty well in the last video, and I don't see any reason that they would be super different today. So if P is a statement, and Q is, or P is a statement, I would eat breakfast, and Q is a statement, I will eat lunch, then not P or Q becomes a statement, I will eat breakfast or I will eat lunch. And if I negate that, I'm basically saying I won't eat breakfast or lunch. Right? P or Q is I will eat breakfast or lunch. And so not that is I won't eat breakfast or lunch. Fair enough. Okay. On the other hand, not P is I won't eat breakfast, or not Q is I won't eat lunch. So let's put that down. I won't eat breakfast, or I won't eat lunch. So let's take a look at these two statements and see if they feel the same to you, if you get the feeling like these two things are equivalent statements. Well, I won't eat breakfast or lunch seems like you're not gonna have anything, right? You're not gonna either have breakfast or have lunch. You're just not gonna eat. That's what that statement seems to say to me. Whereas I won't eat breakfast or I won't eat lunch means that you're gonna skip one of these meals. You might skip both, but it would be okay if you had breakfast as long as you skip lunch. Or that it would be okay to eat lunch if you skip breakfast. And you could skip both, but you just couldn't eat either. So based on that reading of these two statements, it would seem like these aren't the same thing. That there are circumstances under which it would be okay under this statement, but not okay here. And so that would then seem to imply that these two are not the same either. So let's go ahead and formally work this out. So if I were to draw up the truth table for not P or Q, we have statements P, Q, P or Q, and then not P or Q. P can take on the values true or false. Q could take on the values true or false. And so what we have here are all of the possible ways that P and Q could be combined in true and falseness. All right. Now, P or Q is true as long as either one of these guys are true. So when they're both false, it's false, true, true, and then they're both true, so definitely true. All right. And then when I apply the not to that, I don't like the glare in this room. When I apply the not to that, it turns all of these true statements false and this false statement true. So false, 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 true. So if I think about the sentence, I won't eat breakfast or lunch, that's going to be false as long as I eat anything, right? It's only going to be true if I skip both meals. So that makes sense, right? It's false, false, false if I have anything to eat, and then it's true when I don't eat anything. So that seems to match up with what we have here. On the other hand, if I want to look at this statement here, I have P or Q, not P, not Q, and then not P or not Q. And so my possible P's are still true, true, false, false. My possible Q's are still true, false, true, false. And then not P is going to be false whenever this guy's true and true whenever it's false. And not Q is the opposite, right? So it'll be false, true, false, true. Now, when I take the or statements between these two statements, right, I'm just looking for when either one of them are true. So when they're both false, it's going to be false. When one of them is true, it's true. When one of them is true, it's true. When they're both true, it's true. And so here we have it. I won't eat breakfast or I won't eat lunch. Well, if you eat breakfast and lunch, that's definitely a lie, right? You lied when you said that. But if you skip a meal, then that's fine. You said you were going to skip one of them, and you have. Like either you skip lunch or you skip breakfast, and you're all good still, right? And you skip them both, then you're definitely satisfied this. So the truth table for this statement, not P or not Q, does seem to correspond linguistically with what we established here, right? So then I compare this thing to that, and I go, all right, are you two things the same? And I look at them and no, right? They're not the same because there are circumstances under which this statement is true and this one's false, and there are circumstances where this is false and this is true, right? For these two cases where I eat one meal and skip the other, that's okay under the second sentence. It's not okay under the first sentence. So these two sentences aren't saying the same thing. These two sentences are placing different demands on your diet. And so they don't express the same thing. They're not equivalent, right? They're saying different things. So boo to these two things being equivalent. The answer to this is no. All right. So could I adjust this thing here so that it is equivalent? Could I change this somewhat so that this thing and that thing are the same. And we really would like some version of this to be equal to that because, just like in algebraic mathematics, if we have expressions with a ton of parentheses and operations on operations in parentheses, we'd like to be able to simplify that, right? We'd like some version of the distributive rule for this not statement. And right now, if I try to distribute the not naively, that doesn't work. So I have to change this up so that something does. So I'm going to do something very subtle here. And I'm going to ask myself, all right, if I change the or to an and, so that's new, sorry, to an and, now is that statement equivalent? So using my same examples here, my or here is now an and. And let me read these two sentences to myself and see if they make any sense. I won't eat breakfast or lunch. I won't eat breakfast and I won't eat lunch. Those sound pretty similar, right? I won't eat breakfast or lunch means that you're going to skip both, right? I'm not going to have breakfast or lunch. Definitely going to skip them both. And here is saying, breakfast, am I going to eat it? No. Lunch, am I going to eat it? No. And they're both going to happen, right? Because it's an and statement there. So it does feel intuitively to me like these two sentences are now saying the same thing, that you're going to skip both meals, right? And so let's go over here and take a look at our truth tables. This is all the same. And this thing, these are all the same, but this thing, instead of an or, we're going to have an and here. And we're going to ask ourselves, all right, what is the column for this part of the truth table here looking like? Well, an and statement is only true if both of the statements are true. So if they're both false, that's false. This one's true, but that's false, so it's still false. This is true, but that's false, that's still false. This is the only place where it's true, right? Because both not P and not Q are true. So that's the only circumstance where not P and not Q is going to be true. Now, let me compare these two statements, false, 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 true, right? So they take on the same value under the same circumstances, right? For every possible input of P and Q, every possible pair of inputs of P and Q, you get the exact same output for this statement and for that statement. And so this thing and that thing are equivalent. We get to say yes. All right, good. So we do have a rule for distributing not statements through stuff like this. And I'm going to go ahead and erase all of this here. And so this falls under a pair of rules called De Morgan's law. And De Morgan's law governs the distribution of not statements through ors and ands. So we just showed that not P or Q is equal to not P and not Q. And in the handout, actually, I walked through a very similar argument that shows not P and Q is equal to not P or not Q. And so it's nice to have um, laws like this because it will allow us to um, simplify expressions and detect equivalences without going through all of the possible algebra. Now, you might note that because we only have a finite possible number of values for both P and Q, then we can create a truth table with a finite number of entries here. But just because we can do this doesn't mean we always want to, right? It's a process that will work, but it's not necessarily the easiest or the fastest or the least painful way to establish something. So let me give you an example. Is not P or Q and R equal to not P and not Q or not R. Okay, I'm out of the shot now, but that's okay. So, are these things equivalent? Well, I know what this is equivalent to. By De Morgan's law, I can rewrite this as not P, flip the sign, and, right? Remember, what De Morgan's law essentially says is I can distribute a not through two statements and just flip the sign in between them, right? So here I have a statement, here I have a statement, and I have an or between them, like right here, right? And I have a not distributing through, so what I get to say is not the first statement, flip the sign, and not the second statement, right? So this not distributes through. And then not P and by second De Morgan's law, I get to look at here's a statement, here's another statement, and now there's an and in between them, right? And then a not being distributed through. So by De Morgan's law here, I get to say, well, that's going to be not Q or not R. And in two applications of De Morgan's law, I get that this is equivalent to that, which is literally equivalent to that. That's actually the exact same verbatim statement, right? So, yes, those two things are the same. Now, how painful would it be to show that these two things are the same with truth tables? Very. So, let's do that. Hi, everyone. Well, it seems like the QuickTime crashed on me while I was recording the first one, which is just as well. It gave me a moment to kind of erase everything, rewrite this over here, and I'm going to need all of this space to do this terrible, terrible truth table um, of these two statements. Now, just a minute ago, we had shown that these two things are equivalent to each other with De Morgan's law, which is super nice and slick and simple and probably most like the rules of algebra that you're familiar with. We can verify this with truth tables, but we'll understand why this may not be the thing you always want to do. So, uh, let's see here. We have P, Q, and R. Right? Those are the three fundamental statements out of which all of our other statements are made. And P, Q, and R can have values true, false. Right? Q can be true or false, and R can be true or false. And we go through this systematically, where this is by 4s, this is by 2s, and this is by 1s. We get here every single possible combination of true or false between P, Q, and R. And since they have 2 values each, there's 8 possible combinations. So they're all here. And we can show then that this thing and that thing are the same under the same circumstances. So let's try to build this statement here. I already got P, so I need Q and R. So I'm going to switch colors here. To represent the stuff that we're building. So Q and R, we'll just go through the Q and R columns and see when they're both true. So they're both true here, and they're both true here, right? Everywhere else, at least one of these is false. False, 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 right? So then these other 6 entries all have to be false. Great. Next, this statement here, P and Q and, or P or Q and R, sorry. So P or Q and R, we look at P, we look at Q and R, and we say, okay, when is either one true? So true, 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 true. Now, these are all false here, but that's still true there, and then false, 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 right? So it's false here when they're both false. Right, so let me space this out a little better. True, 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 false, true, false, false, false. All right. True when P is true. True when my rows are getting kind of messed up here. When Q and R is true, and then false when they're both false. Great. Then it's the nut of that whole shebang. And so it's just false whenever this is true and true whenever this is false, right? So when I'm building this column, it's pretty straightforward. False, 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 true, true, true. Great. So that settles it for this statement here. All right. I'm going to switch colors and build up this guy. So I need not P, not Q, and not R, right? Because I have not P, not Q, and not R here. So not P will take on the values false, 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 true, 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 right? False and then true. Not Q will go false, false, true, true, false, false, true, true. And then not R will be false, true, false, true, false, true, false, true. Great. Then add the statement not Q or not R, which is true when either not Q or not R is true. So false, because they're both false, true, 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 false, true, true, true. And finally, not P and not Q or not R. And that's going to be true whenever not P or not Q or not R are both true and false otherwise. Right? So let's see. False, 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 true, true, true. And so finally, we're comparing this column to this column And we're asking ourselves, all right, great. When are these people and these people here the same value? Well, false, 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 true, true, true. So they do in fact take on the same value under the same circumstances. So these two statements are in fact equivalent. But look how much more work it was to establish all of this, and look how complicated it got, and how easy the possibility to make minor mistakes that would screw this up. Right? That's all sort of not fun things. And of course, you can avoid the mistake part maybe by using Sage to compute the truth tables for both sides and just comparing those, which is a perfectly fine way to do it. But even writing those things out in Sage probably would take less work than applying to De Morgan's law in the first place. The De Morgan's law is a fairly clean and, well, nice way of evaluating these not statements. So hopefully this lecture here has given you two things. One, an understanding of how we determine when two things are equivalent or not equivalent. And second of all, how we could apply De Morgan's law to make this process of equivalence easier to handle and get our heads around than using truth tables all the time. Well, we will have to do some extent of truth tabling inevitably in all cases, but um, and it's unavoidable in the long term, but it's avoidable in a lot of circumstances. And when we could avoid it, maybe we should. So that's that. Thank you for watching. The next lecture will be about implications.